Okay, solving exponential and log equations. So we'll see the list of rules, solving exponential equations, logarithmic equations, how to find inverse functions, and finally some interest problems. So this is the list of rules, logarithm identities and rules. The fundamental property is this. Log of 1 is 0, log of the base is 1, inverse identities, one-to-one rules, product addition rule, quotient subtraction, power coefficient, change of base property. So solving exponential equations, we can use these various rules to solve equations, but some exponential equations, you don't actually need to use any logarithms because you can rewrite them in terms of the same base. So if we're looking for this, we can say, well, we know 1 over 49 is 1 over 7 quantity squared, which is 7 to the minus 2. So we can rewrite this equation as 7x squared plus 3x equals 7 to the minus 2. And one of the rules that we have is that if we have the same base, b to the x equals b to the y, then x must be equal to y. So we have the same base here, so that means that we must have the same exponent. So x squared plus 3x must be equal to minus 2 because we have the same base and they're equal to each other. And this is a quadratic equation. It can be factored. And that gives us our solutions. X equals minus 2 and x equals minus 1. And you can check the solutions by plugging them back in to see if they work. All right, this is a similar thing. We know that 8 is equal to 2 cubed. What does that mean? That means 8 to the 3x minus 1 can be rewritten as 2 cubed to the 3x minus 1. And using one of our exponential rules tells us that 2 cubed to 3x minus 1, I just multiply these exponents together and I get 9x minus 3. So 8 to the 3x minus 1 is 2 to the 9x minus 3. And so that means our equation becomes 2 to the x plus 3 equals 8 to the 3x minus 1. That's the equation we started with. That's now 2 raised to the power 2x minus 3 equals 2 raised to the power 9x minus 3, because this is equal to that. Same base, so the exponents must be the same. This is a plus 3. So we'll add a 3 to both sides. Subtract a 2x from both sides. And divide by 7 to get my answer. Okay, now the fundamental rule, remember the fundamental rule is a way to, or property, is a way to convert from exponential equations to logarithmic equations or vice versa. So that helps in solving a lot of equations. To use it, what you need to do is to isolate the exponential or logarithmic term all by itself with no coefficient. So to solve this using the fundamental rule, we have to isolate that term. So it means subtract a 3 and then divide both sides by 7. And now we have that set up for the fundamental rule. And the fundamental rule tells us that something raised the x equals m can be rewritten as log base b of m equals x. It takes something in the power and moves it to itself by itself on one side of the equation. So what does that give me? Natural logarithm of 9/7 equals 2x plus 7, right? We're using this as m. My base is e, so remember that log base e is natural logarithm. And now we can solve this for x. Log of 9 over 7, that's some number, is 2x. And then I can multiply both sides by 1/2. To get x, whatever number that turns out to be. Okay, and now some exponential equations can be solved in a number of ways because it doesn't really matter which base you use. So we could do this in base 10 algorithms. And this will require the power coefficient rule. We'll take log of both sides. Power coefficient rule tells me that these exponents can come out front as coefficients. So 2x times log of 3 equals the quantity x plus 1 times log of 7. Remember that these, log of 3, log of 7, those are just numbers. Like e or like pi, they're complicated symbols, but they're just numbers. So we want to solve this for x, get x by itself. So how do we do that? We will distribute the log 7 on the right. Move this term over to the left by subtracting an x log 7 from both sides. And then I'm going to factor an x out of the left side. And then finally, we can divide both sides by this entire thing. So that gives me log of 7. That was on the right side, divided by this coefficient, 2 log of 3 minus log of 7. This is all in base 10 logarithms. Every calculator has a base 10 logarithm, so you can go ahead and calculate that and see what number you get. And that'll be your solution. Of course, you can do the same thing using base 7 logarithms instead. Take log base 7 of both sides. One of the rules we have is that log base b of b to anything, if this and this match, that's just whatever the exponent is. So the right-hand side is just x plus 1, because this is base 7. And the right-hand side, we can use the power coefficient rule, pull out the 2x again. Right, and now we need to solve for x. So same kind of thing, we need to get all the x's on one side, all the terms without any x's on the other side. So we'll subtract an x from both sides, factor out the x, and then divide through. Right, and that will be, if you have a calculator or Microsoft Excel or something on a computer that can do log base 7 of 3 and grind out what that number is, it's the same number that you would get here. And then finally, you can solve this using the fundamental rule, but we need to be able to do this, we need to rewrite this as a base raised to the x to the m. We don't have that yet, but we can do a couple of things to prep it into that form. 3 to the 2x is 3 to the 2 quantity to the x, right? Because these are multiplied together, so we can stack them like that. That's the same thing as 9 to the x. That's the left-hand side. The right-hand side is 7 to the x plus 1, and that's the same thing as 7 to the x times 7. Great. So we can rewrite this equation then as 9 to the x equals 7 to the x times 7. Divide both sides by 7 to the x, you get 9 to the x over 7 to the x equals 7. Or finally, you have 9 over 7 quantity to the x equals 7. So we have it rewritten like this. And the fundamental rule tells me then that x is equal to log base b of m. So x equals log 9/7 of 7. And so there you have it. So why are these three things all the same number? Here's one, here's another version, here's another version. They're all solving the same equation. So why are these all the same thing? So if we take the answer in 4a, right, that's log of 7 over 2 log of 3 minus log of 7. Those are all base 10. We can condense the denominator into log of 9 minus log of 7, because the 2 can go into the 3 as an exponent. That gives me a 9 there. And then we can condense it even further. Like that. And this now is the change of base theorem. If I have a log divided by a log, right, in the same base, this is both base 10. Where's my change of base theorem? There it is, right? Same base. I can rewrite that as log base b, that's this thing, of m. So change of base tells me that this will be log base 9/7 of 7. And that's the same thing as this. For b, gave us this 1 over 2 log 7 minus log base 7 of 3 minus 1. And we can rewrite that. Remember that 1 is log base 7 of 7 raised to the 1 power, because 7, same base, it just becomes the power. And that's log base 7 of 9 minus log base 7 of 7 to the first. So we can rewrite 1, both of these, as log base 7 of 7 to the first power. And then the 2 goes in on the 3 as an exponent. And then we have log base 7 of 7 over log base 7 of 9/7. And we're exactly the same situation as we are here, except that we have base 7 instead of base 10. So the change of base theorem tells me that's also log base 9/7 of 7. And the actual number this is, if you plug it in and grind it out, is about 7.74. So logarithms are pretty flexible to solve equations. If you want to get something that's in the exponent out of the exponent, you have to use a logarithm at some point. Which base you use doesn't really matter. Base 10 and base E you have is on every calculator. If you have calculators that can do other bases, maybe another base would be more would be simpler. Okay, so solving logarithmic equations, we have to keep in mind that only positive numbers go into logarithmic equations. So remember to check your answers by plugging them back in. This one, we're just going to contract the right-hand side. Right, remember that the 2 can go in the 5 as an exponent. That gives me a 25. The 1/2 can go in the 16. 16 to the 1/2 is square root of 16, which is 4, and then minus log 10. So what do we have here? A plus and a minus. So I'm going to have 25 times 4 divided by 10. And that's equal to 10, because 25 times 4 is 100. So condensing this, the addition becomes a multiplication, the subtraction becomes a division, And these three logarithms tied together as one logarithm like that. So x equals 10, because if you have log of something equals log of something else with the same base, then the things inside the logarithm have to be equal to each other. So x equals 10. Okay, so this one we need to prep a little bit. The subtraction tells me that this is going to be, could be written like that. Fundamental rule again, log base b of m equals x means that b to the x equals m. So here, m is the thing inside the logarithm. The base b is 10, and x, the power, is 2. So if we rewrite this using the fundamental rule, we get base, which is 10 to the power, that's the 2, equals x plus 1 over x minus 2. And now we need to solve for x. So 10 squared is 100. It's supposed to be x minus 2, x plus 1. Multiply both sides by the x minus 2. Going to get all my x's on one side by subtracting an x from both sides, and all my numbers on the other side by adding a 200 to both sides. Then I get x over 201.99. Does it work in the original equation? Well, if I plugged in 201 over 99 in here, I'll get a nice positive number. 201 over 99 is a little bit bigger than 2, so that number minus 2, that'll also be positive, so it works out. So we're in good shape there. Okay, what about this one? Log base 2 of x plus log base 2 of x plus 2 equals 3. So we can combine this using the multiplication rule. And now we can use the fundamental rule. 2 cubed equals whatever's inside my logarithm. And that's a nice little quadratic. You can factor that. That would be plus 4x minus 2 equals 0. And that would suggest that our solutions are x equals minus 4 and x equals 2. This is a little bit suspicious, though, because does that fit in the original equation? Is that true? And you can't have negative numbers inside a log because the domain of logarithm is only positive numbers. That's an n, that's a t. So it doesn't work. Why did we get minus 4 as an answer? Well, when we did this step, right, when we combined them, this would be minus 4 and minus 2. And when we combine them by multiplication, the minus 4 times the minus 2, the two signs cancel out. So we have to be a little bit careful in using these rules. The rules only work as long as you can actually calculate the logarithms without the combination, right? So log of minus 4 and log of minus 2 don't exist, so you can't use that as a solution, even though if you plugged in minus 4 here and here, the minus signs would end up canceling out. So not a solution, that's our only solution. You have to be a little bit careful with these quadratics. So another quadratic, log base 3 of x times 6x plus 7 equals 1. Fundamental rule, 3 to the 1 equals x squared, 6x squared plus 7x. Or finally, 0 equals 6x squared plus 7x minus 3. Remember our quadratic formula, there's A, there's B, there's C. X equals negative B plus or minus the square root of 4ac, B squared minus 4ac all over 2a. So X equals negative 7 plus or minus the square root of 7 squared, which is 49, minus 4ac, 6 times, oh, let me undo that. It's 4ac, and I forgot to write in the 4, minus 4 times 6 times minus 3, all over 2a, which is 12. And as I usually do, I'm going to break this into two fractions, minus 7 over 12, plus or minus 49, 12. So minus minus becomes a plus. 4 times 3 is 12, times 6 is 72. And that's over 12. And that becomes a 121 inside. So we get X equals minus 7 over 12, plus or minus 11 over 12, because square root of 121 is 11. So that gives me two solutions. One is minus 7 plus 11, which is X equals 4 over 12, which is 1/3. And the other one is X equals minus 7 minus 11, which is minus 18 over 12, which is minus 3/2. Right? And we have an X by itself there, so not a solution because it's negative. So our only solution is going to be this. So we use the product rule to pull this together, and then the fundamental rule to get the stuff that's inside the logarithm out of the logarithm. So finding inverses, right? Here's a function. We want to find the inverse. And usually, again, this is going to be the fundamental rule. How do we find the inverse of this function? Isolate the exponential term. And then we can use the fundamental rule because we want to be able to write it like that. And then once we have it written like that, we can use the fundamental rule. So subtract a 5 from both sides. And then we'll divide both sides by 2. And now we've got something. This is my m here. And then an exponent, 3x minus 1, and my base is e. So the thing in the exponent, the 3x minus 1, that becomes natural logarithm of y minus 5 over 2. Because base e logarithm is ln. And now we just want to solve for x. We'll add a 1 to both sides. And then we'll divide both sides by 3. Right? And dividing both sides by 3 is the same thing as multiplying by 1/3. And then finally, we'll switch the y and the x. X minus 5 over 2 plus 1. And that's the inverse function to that function. Same thing here. Isolate the log term because to use the fundamental rule, we need to use log base b of x of m equals x. So we need to get a log term all by itself. So we'll add a 5 to both sides. And then divide both sides by 3. Now we have it set up in this formula, and that gets turned into b raised to the x equals m. Our m is the thing inside the logarithm, that's this. Base here is 10. Remember that if it doesn't say the base, it's 10. and then x is whatever's on the other side. So we have 10 raised to the power 5 plus 5 over 3 equals 2x plus 3. Now we want to isolate the x. So we'll subtract a 3 from both sides, and then multiply both sides by 1/2. And then finally, we can switch the x and the y so that it's written y as a function of x, which we like. And so there we go. There's our inverse. Keep in mind that if I multiply the 1/2 through, 1/2 times 10 raised to a power, you can't simplify anything because you have to do the exponent first. And since we don't know what x is yet, you can't actually do anything with that until you know what that exponent is. So this 10 and this 1/2 don't cancel to give you a 5 in any way. And then finally, we know that interest problems, whenever we want to know how long, that means we need a logarithm. So here's an account compounded monthly, that's 12 times a year. So we need the formula A equals P 1 plus R over M raised to the MT. And what do our letters stand for? Well, I usually write them down like this and start filling them in. $3,000 was put into the account. That's how much she's saving, and so that's her principal. We want to know when there'll be 5,000, so that's sometime in the future. Interest rate is 4%. It's compounded monthly. That's 12 times a year. And T, we don't know what T is. That's what we're trying to find. Plug everything in, you get 5,000 equals 3,000. 1 plus 0.04 over 12 to the 12t. So to solve this, I want to use the fundamental rule again. And so I'm going to isolate this term by dividing both sides by 3,000. That gives me 5/3. And then the thing inside the parentheses is 1.0033. The 3's just repeat. That's quantities of 12t. So there's sort of two ways to do this. One is a fundamental rule calculation. Here's our base, here's our power, here's our thing on the other side of the equation. So we get log base 1.0033 repeating of 5/3 equals 12t. Divide both sides by 12. And you can solve for t. The other way is to go base 10 or base e, because those are things on your calculator, and use the power coefficient rule. So take log of both sides. So that's just log of both sides. On the left side, you just have log of 5/3, whatever number that is. And then now we can pull the 12t down. Great, so now we can divide both sides by this number. We'll get log of 5/3 over log base 10 of 1.0033 repeated equals 12t. And then finally, we can both divide both sides by 12. Equals t. So this is supposed to be all one bar there. Great. By the change of basis theorem, we know that these two parts, this logarithm part and this logarithm fraction, are the same number. So depending on what kind of calculator you're using, one that's can do these kinds of bases, you can use that. If you just have base 10, you can do that. In any case, t turns out to be about 12.79. So about 12 3/4 years, about 12 and 9 months. So same issue. She puts in $3,000, wants to know when it's 5,000. Same interest rate 4, but now compounded continuously. So compounded continuously means we want A equals P e to the RT. What's A, P, R, and T? Remember that E is just a number. So she's investing 3,000. She wants to know when she'll have 5,000. The interest rate is 0.04. T, we don't know what that is. 5,000 equals 3,000 e to the 0.04 t. And again, to do the fundamental rule, we have to isolate the exponential term first. So we'll divide both sides by 3,000. 5/3 equals e to the 0.04 t. And now we like this very much because if we use the fundamental rule, we get log base e, which is ln, 0.04 t. And so this is on our calculator. So this is actually whatever calculator you have will have an ln button. So 1 over 0.04, multiply both sides by 1 divided by 0.04, log of 5/3 equals t. And you can grind that through your calculator and get 12.77 years. So compounded continuously means you're compounding interest a little more often than you are by doing monthly. And you don't gain a whole lot of time, 12.77 versus 12.79. 0.02 is about a week. So it will double a week earlier. It'll get to 5,000 a week earlier if compounded continuously than compounded monthly. And so that is how to solve equations using the log rules.